Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about wireless power transmission. So let's dive right into it. Now, this is the dream that almost everybody has at some point in time. And the idea is basically we're no longer going to need high tension lines. Now, do not ask me why it's called high tension line rather than high voltage lines. I don't know, so ask something French or something. But the idea is if we truly achieve this, we will never need to quote unquote plug things, meaning you drive your electric car into your garage, the end, done, walk away. It will charge automatically. And again, sometimes people even have even grander dream, meaning you're going to have a road and you're going to drive on it, and that's the end of the story. Why? That's it. The road is charging your car, so you do not have to worry about range. Range is as long as there is road. So we have a lot of dream, and this dream starts from Nikola Tesla. Now you have to understand, whenever somebody pulls things like this, like they laughed at Nikola Tesla, or it's a dream of Nikola, be very cautious at that point in time. Like apply some serious brakes at that moment in time, because you have to understand, Nikola Tesla is standing on the shoulder of giants before his time. Basically, people who did R&D before him, he collected that information, he did amazing work on it, and then again, engineers now take his work, build on top of it. Engineers tomorrow will do the same. That's the whole point. That's how you brick by brick, brick by brick, we keep progressing. Same applies on Newton, same applies on Stephen Hawking, Richard Dawkins, Einstein, all level. But that's the same thing. But here's the deal: there are some limitations. He had amazing ideas. There is no denying that. He did amazing work. No denying that. But here's the deal: not everything that came out of his mind was wise, because he also thought of Tesla turbine. He physically built it. It did not work. That's why we do not use Tesla turbine. Everybody is like, Tesla turbine is more efficient. It's like, here's the deal: if it really was efficient, every power company will say, shut up and let me build it. Nobody hates efficiency. Nobody hates money. So everybody would do that. But why did not Tesla turbine succeed? The RPM it requires is so goddamn high. First, it would have a very serious problem in terms of getting frequency of main lines. But if you spin anything at that kind of ludicrous RPM, it will shatter any material, including modern carbon fiber will not be able to hold it. So RPM is a serious limitation. And that's why, like, he built a prototype, then he realized, yeah, it does not have that oomph that he was thinking. On paper, it made sense. The moment you come to physical reality, it did not. And same goes with this. At his time, people were so backwards, again, in terms of understanding. Not enough people, smart people, have did their R&D, that nobody understood electrons properly, atoms properly. Like, there was some vague idea, but nobody like, okay, this is the maths of it. And specifically one crucial rule: inverse square law. He had no concept of that. Nobody had figured that part out thoroughly yet. People had a rough idea. It's like, I think intensity does go down, but what's the math behind it? Nobody knew at that point in time. So when he's holding that wirelessly powered lamp, he was thinking, hey, it works. He assumed if I build it big enough that it's going to work over a few kilometers. That made logical sense. But again, without inverse square law, you have no actual idea like how much oomph you have to put on A to transmit over 10 kilometers. That exponential loss, he had no idea of calculating. That's why that idea never worked. Again, nothing wrong with him. He made amazing things. It's just like not everything that came out of him was, amazing. And that same applies on Einstein also. Not every equation he came up with was like, whoa. Sometimes he literally messed up his own equation because it did not make sense to him. So that's human. We are all human. Good humans, bad humans, dumb humans. We are just human at the other end of the day. So what about physics? I have specified this time and time again. No matter what you talk about, there's always three layers to everything: physics, engineering, and economics. And economics is the granddaddy layer. Now, before you go to the granddaddy, you have to figure out the main daddy, that is physics. Does physics allow it? Meaning, if you are like, I'm going to use this and this puppy is going to be like traveling faster than light speed. No, physics is like, no, brother. Nope. Nope. So physics is the first layer. Now, does physics allow wireless energy transmission? Absolutely. Again, we had experimental proof back in the Tesla days, so we know physics does allow it. What options do we have? Well, we have first option, that is electromagnetic induction. Exactly how a transformer works. Think of it this way: like if you put a continuity meter between low voltage side and high voltage side, you'll find they are not connected, meaning low and high are not connected. They are inherently wireless. How the heck they are transmitting power? Electromagnetic induction. The only difference between that transformer and this is the core. Core is there for efficiency purposes. It does work. The electromagnetic induction does work awesome, GG, but it does have lot of capacity, meaning you can transfer megawatts, gigawatts, even terawatts if you really want to. So that's the amazing part. But it does not work over large distance, meaning even if your transformer you are designing and you have to make it very large, people will like, what, split that transformer into multiple subunits. Like you will find that in HVDC units where they are like, if it's a 12 gigawatt unit, they will not make one 12 gigawatt transformer. They will have like one phase 12 gigawatt, another phase on all three combined makes it. Because again, if coil A and coil B becomes too far apart, it does not have coupling efficiency. So you need laminated metals in order to reduce eddy losses and improve efficiency, coupling efficiency. It does work with the core. But here's the deal, what if you remove the core? What if you made it truly like mobile wireless, like exactly how your mobile phone is? There is no core connecting the transmitter coil to your receiver coil. It does work, but it's very inefficient. So your normal transformer would be like 98% efficient, and in a really cold environment could be almost 99% efficient. This puppy, you will be lucky at it's 30% efficient, especially at distance. The more the distance you add, the exponentially this loses. Meaning the moment you open your mouth and you're like, I'm gonna inductively couple energy from A to B over long distances, they're like, dude, this guy does not know maths. Fundamentally, it does not travel far. It will do, like if you do lab scale test, everybody will, yeah, it just works. The moment you add kilometers to it, yeah, forget about it. You have to put terawatts of power to get kilowatts of power on the other end. That's how much wastage will be there. Exponential, inverse square law, exponential wastage will be there. Then this is for like short duration, short distance communication, meaning if you have things almost touching each other. That's awesome. But what if you really have to go through kilometers, hundreds of kilometers, or 36,000 kilometers? I'll talk about that in the future. You have to convert it into what we call electromagnetic waves. Everything is electromagnetic wave. Basically, your infrared, electromagnetic, optical, electromagnetic, X-ray, electromagnetic, gamma, electromagnetic radio, electromagnetic microwave, electromagnetic. So you have to convert electricity into a format of electromagnetic wave. Now, because of the variety in the wavelength, you have different pros and cons. Everything will give you something professional, something consequential. For example, if you are like, hey, what if you use photons in the visible spectrum, basically optical spectrum, it's like awesome, but here's the deal. People can see it, that power transmission, and if it's multi-megawatt, it will glow like a multi-megawatt light bulb. Nobody likes that. So it's like, okay, we cannot use something that we can directly see. How about infrared? We can't see it. It's real. We can feel it. It's hot. So fundamentally, yeah, that's not also a good thing. You do not want that. What about microwave? It can pass through us without dumping too much energy into us. That's awesome. It does me. So can we use microwave? Yes, this is NASA's trial of like actually transmitting multi-kilowatt power from basically this dish to this rectina, and this did work. It's like a known tested technology. So you have a lot of option when you convert electricity into some sort of electromagnetic radiation. Optical, microwave, millimeter wave, that's up to you. You can go YOLO on it. So this does allow you to bypass the distance limitation of inductive coupling. That's the one benefit of going to this system. Efficiency is low, but you do get distance. So what's the problem here? Like again, physics does allow it. We have been doing it from 1970s. So what's the problem? Well, all photons have effects on things, meaning many times we have this sort of partial understanding of photons. It's like ionizing radiation is bad, everything else is okay. Not true. The only core vector is that amount per surface area, meaning if I say 100 watt of photons, does not mean anything. If I say 100 watts of X-ray, it's like, oh, dangerous ionizing. No, not really. Like, what is the instant? Like, what is the surface area? If you go outside in the sunlight and 1 kilometer square, 100 watt of X-ray is there, nobody cares. Gamma rays, nobody cares. That's the whole point. Amount per surface area. If I take the same 100 watts of energy and put it into, like, let's say a small torch like this, you can see it can set things on fire. If you expose it through your skin, it will burn it directly. Not even indirectly, oh, it might do damage. No, it will just set you on fire. And same goes with everything else. Microwave, not an issue. If it's low enough, meaning that's how our mobile towers work, that's how communication networks work, that's how majority of things work. We don't have an issue here. Why? Intensity is low, meaning amount per surface area is very low. Now you can take the same amount of energy, let's say 4 and 5 kilowatts that are used for mobile towers, and you concentrate that to, let's say, 1 millimeter square. Yeah, that's James Bond level death ray. That's flat out death ray. So you have to understand this core aspect. Do not focus on what photons they are using. Focus on what is the intensity of it. Meaning, if they are saying we're gonna transmit like 5 kilowatts from A to B, that means there is 5 kilowatts of photon bandwidth here. That is brutal. 5 kilowatts of photons there. Does not matter which spectrum it is. Of course, different spectrum will be absorbed differently. But if you have that much in it, it's like a old military saying of brute force. It's like if it's not solving your problem, that means you're not applying enough of it. And if you have 5 kilowatt, does not matter which spectrum it is. That's enough. That's like, we got this. You are talking about like 5 kilowatt, 100 kilowatt. Think of it this way, like we have optical light lasers that cut through things, cut through metals, cut through multi-inch thick metals, just because we can make that amount per surface area so small, so small. That's the whole thing. Now, That's the physics aspect of it. Another aspect is it's not really that efficient compared to normal transmission, right? Flat out not very efficient. And the inverse square law still applies. Again, if you may be like, I'm gonna laze it and all that, just again, it will slow it down, but it will still apply over a very long distance. So longer the range, more inefficient it becomes. Meaning, if you have, let's say, 10-kilometer distance, it's good, it's some sort of viable. But the moment you're like, let's say, offshore wind farm, which could be like at least 100 kilometers away from the shoreline, yeah, no. And if it's like 36,000 kilometers away, really no. So this is one thing you have to understand. The efficiency goes down drastically over distance. It can extend for much longer compared to inductive system, but still has limitations. And all spectrum, if you have basically all spectrum becomes dangerous if you have too much oomph into in a very small area. That's the point. That's the whole point. Flashlight, normal light, and it does not even have incandescent, so it's releasing infrared. It's just normal optical system. Basically, if you ever notice floodlight, if it ever came up too close to you, you're like, dude, it hurts. That's the whole point. Too much photons in too close of area. So what about the economics of it? The granddaddy layer. The granddaddy layer is simple reality. You are a power plant owner, whatever it may be. Maybe it's coal power plant, maybe it's geothermal power plant, maybe it's solar, maybe you are producing energy. Awesome. You have to sell it. The more inefficient you become, the more lost revenue you have incurred. Meaning, if you are making 1 gigawatt, awesome. You are selling it like, and by the time customers are getting, they are only getting 700 kilowatt. They're like, dude, 700 megawatt. They're like, dude, 300 watt lost revenue, meaning it will actually hurt you economic sense. It's brutal because you have to understand one core aspect. You are paid by the unit sold, not produced. If you are going to, let's say, a household, it's like, bro, your electric bill is, let's say, 500 units of electricity. Awesome. They're like, okay, this is the charge, I'm gonna pay you. Now you're like, actually, bro, it's like 500 come to your house. That means from power plant, basically the person who was actually paying for the fuel of it is like, they had to produce 600. Like, I don't care. Everybody's going to say that they don't care. That's why we want to be as efficient as possible to reduce lost revenue. So what companies do is like, they will try to make it as efficient as well. Again, there are some laws of physics. You can't really be that efficient. So they'll like, okay, per unit production cost is, let's say, X. Customer wants to pay for X, but here's the deal. You have to have some buffer. So like X by 30%. That is the maximum that people are. But if you start to make that percentage into multiplication, meaning if you're consuming 500 unit and somebody has to make, let's say, 10 times more than that to transmit that energy, yeah, good luck trying to collect money on that. It's like, people like, no, just no. That's the whole thing. And wasting resources is unwise. For example, recently there was a lot of hype in aluminum air battery, and I specified it's the worst battery simply because it has 20% efficiency. Now what people did not get most of the time is like, batteries are 100% efficient when you are running on 80-90% efficient. Yeah, that is true. Here's the aluminum air battery is a disposable battery, meaning you use it, you throw it away, or you have to recycle it. And recycling is not same as recharging. Recharging is very efficient, recycling is not. Now, like, aluminum is very efficient to recycle. That is true in the wild because it only oxidizes on the surface. When you put aluminum in a battery, it oxidizes to the core. Basically, you try to oxidize every single atom. That's how you're getting your electricity. So you want to oxidize it, but once you oxidize it that much, the recycling efficiency goes away. So basically, naval corps, and there are many other country, government, army, all of them did the math. Math was like, you are lucky if you get 20% efficient, meaning put 1 megawatt in, the battery that will come out of the system will be best case scenario 200 kilowatt. You are just burnt 80 kilowatts, 800 kilowatts of electrical energy, just lol. That's why the wasting of that energy is unwise. And you will like, oh, we have solar panels. Yes, deal. Solar panels physically take money, physically take space. They take copper, they take everything else. They take inverters. None of them are cheap. You cannot afford to waste things. It's flat out unwise. And right now, realistically, all you will be doing is burn more coal. Really not wise. So it is true, this sort of high transmission, high tension lines are very expensive, undeniably so. But they pay for themselves. That's why people erect them. That's why you will find them even in a densely populated city. Either it will be underground or it will be there. You will always find them. Why? Because they do pay over time in terms of basically lifelong. Meaning, once you build this, the pipeline efficiency that they give you, it's so high that it's like, yeah, it's worth it. Yeah, it's costing a lot of money, but because you are not losing revenue, you're like, yeah, I can pay for it. It does work exactly the same way. And think of it this way, this high voltage AC lines, they do work. but they are not efficient enough, and world is moving away from this to HVDC, high voltage DC lines, which saves 3% more. So if you ever Google HVDC, you may end up articles that are saying HVDC is 50% more efficient. What does that mean? It simply means is that if you have 100 kilometer of transmission, let's say you are transmitting power from A to B and it's 100 kilometer, how much energy is just going to be lost from pole to pole? Basically the transmission poles, it's around 6% per 100 kilometers. So if you have sent 1 megawatt, 6% poof. But if you had high voltage DC line, you will able to send around 3% more. Basically loss would be 50% less. So country, and again HVDC is very expensive, so generally it's preferred to do on long range where the distance is significant. For example, in China's case, it's around, if I'm not mistaken, 1200 kilometer. Other some European countries have distance that are like around 750 kilometers HVDC links. India also has a world's first tri-link system, meaning A, B and C multi-point connection, that is in Agra East system, that is around 800 ultra high voltage DC, and it's around 8 gigawatt capacity. Range I'm not sure, but it's like few hundred kilometers also. So people are that serious about saving energies. That's serious because again, even though it's expensive, but you lose less of it, that translates to more profit. People will do it. It's wise to do it. And you are talking about like, let's waste 30% of it. And if anybody talked about any sort of optical conversion, A to B, and they're like, as in like photon conversion, and they're like, you know, it's 100% efficient, they're lying or they're removing some detail. For example, the video that triggered me to make this one, literally they said, this is 100% conversion efficient. I'm like, physics does not allow that. You are removing some. Then they're like quietly saying, yeah, that's the receiver efficiency. Transmitter loses 30%. I'm like, that little bit, like here we are trying our ass off to save 3%, and you're like, we just lost 30% of it. Economics does not work, and that's the granddaddy layer. Now, what I can hope in the future? Well, here's the deal. There are some places where wireless electricity does make sense. That's absolutely true. There's no denying that, where it makes sense. But you should only use there. For example, space-based solar power. Now, space-based solar power is getting some serious attention. My expectation or my understanding of the situation is like most people have given up on fusion. It's like it's not happening anytime soon. So Japan, USA, they're doing some serious R&D. And again, USA already did research on that in 1970. They had the largest actual physical scale test of it. And the idea is that you're going to have multi-gigawatt satellite in geostationary, because that will be in the sun majority of the time. Majority as in like 99.99%, or 70-minute dark time will happen like 2 times a month, 2 times a year. But majority time is like working power plant. So they're going to transmit power. Now you're like, okay, are they transmitting, how they're going to transmit the power? Microwaves. Now wouldn't that cook anything in the vicinity? No. Why? Photons per unit area, because even if they try to lace that puppy, by the time it touches Earth, it would have been traveled 36,000 kilometers and would have expanded into a circle that is 6 kilometers. A circle in the diameter of 6 kilometers. The density at that point in time is barely 10 watts per meter square, or sometimes even lower than that. Or some, again, you can try to concentrate it, but that's low enough that if a plane goes through it, does not care. If a bird flies through it, does not care. That's the whole point of it. That's why, you know, it makes sense for that. Again, it does have the consequence. Large surface area had to be done, but again, we already have solar farms that are multiple square kilometers. So again, it does make sense. Like space solar is amazing technology for that. Medical implants, that's another aspect of things. Basically, we used to have radioactive power sources for medical implants, but again, people did not dispose of it properly. Hazards happen, and then company just like, okay, I'm out. We're not going to put plutonium in your pacemaker, which will allow you to, like, especially it's a really brutal for our children. If they have to need pacemaker, then it's like they have to again and again every 10 years. Now everybody's like, hey, what if we use inductive coupling? Yes, it's going to waste energy, but it does make sense, much more efficient than so it makes sense. That places wise use. For example, underwater remote vehicles, they try to be as sealed as possible, because anything that is electrically conductive will corrode exponentially. So they try to coat everything and then use inductive coupling to transfer power. Makes sense. Awesome technology. So there are use cases for basically wireless energy transfer. It just does not have to be in our grid. It does not make sense. It just pollutes more. So that's the whole point. And when this company, the EMROD company, they're talking about like, we're gonna have this in emergency. I'm like, can't you just airdrop a normal ruggedized generator that will give far more power, far more cost effective, and you can just keep fueling it. Again, they are showing this sort of image that, you know, if terrain is hard to cross, it's going to cost a lot. That's absolutely true. But here's the deal. Imagine that electrical company is like, sir, we are sending, generating 1 gigawatt. They're like, awesome. How much we are selling to the customer? Sir, 700. What happened to the remaining 30? Yeah, that transmitter lost it. Lost it as in like waste heat. Think about it. And that's a recurring loss that you have to account for as long as you are. Like, it literally would, over a time, it's like, dude, it would have been cheaper. Again, it may not happen on year 1, but at year 10, it will like, wouldn't it have been just cheaper if I just took out a loan, did this, and just be done with it? And not to mention, now AC line does require 3 cables. You can have DC system that can have 2 or even 1. You can just do it, which we call monopole HVDC. You can just transmit it, and it's like done. And this company, they are using millimeter wave. The shorter the wavelength, the shorter the distance. They are like, we're gonna have transmission, then we're gonna have relay, then we're gonna have rectina. I'm like, they're only saying that retinas are very efficient. That is true, absolutely. That's what NASA was trying. But here's the deal: the transmitter is losing energy and the relay is losing energy. So from power plant to your household, it's losing so much energy that you have to burn so much more fossil fuel that we're gonna become fossil fuel because of that. So that's the whole thing that really frustrates me. It's like everybody's removing that part that economically does not make sense. That gives me hope that nobody's gonna do it, because again, the moment people start to lose money, it's like, nope, thou shall cancel it. So again, it's amazing technology. It's really awesome if we really employ it wisely. Medical implants, underwater systems, basically solar, space solar, amazing things. But it's like using it for power grid, it's like everybody's gonna hate it. And not to mention, they literally talked about, it's like, if a bird flies through it, they're gonna cut the power. I'm like, do you really want that sort of power delivery system where it's like a bird flies through the beam? Because I specified, it does not matter which spectrum. Only thing that matters is like how much oomph is there. Like the panel were like, they were showing us this big, and it's gonna have like few kilowatts. Yeah, no, that much photon is like, no, just no. So that's my hope. I hope this video have clarified certain aspects for you guys, hopefully. So this was my presentation on wireless energy transmission. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.